Hey, today we're going to talk about a dead guy by the name of Sir Isaac Newton. Sir Isaac Newton, you've probably heard of him. You've probably heard of him from your math teacher. Well, that's a good thing because he did a lot for math. He did a lot for physics as well. As a matter of fact, he advanced the math in order to better understand the physics that he was studying. One of the things that Sir Isaac Newton really studied was motion. And he had three key statements about motion that today we call Newton's laws of motion. And these key statements just state the facts about what happens when we're talking about objects that move. And in order to make them easier to remember, instead of calling them by fancy names, we call them Newton's first law of motion, the second law of motion, and you'll never guess the last one. It's the third law of motion. These are the names that we give them. Physicists are not very original. We're not famous for, coming up with cool names. We could hire some people maybe to come up with better names than we do. But for our purposes, and for the test, it'll be a lot easier to remember first, second, and third. Before we get to these laws of motion, though, you need to understand a concept called force. And to help us understand force, I have a little tool here. Most of you know this tool by a different name, ball. That's okay, you can call it what you want. It's a tool. Force is something that makes the ball move. There are two things that I could do to this that would cause it to move. I could either push it, or I could pull it. Grab onto it and pull it. So a force is either a push or a pull. It's something that causes something to move. So, if you're asked to define force, one of the simplest definitions of force is that it is a push or a pull. Force is a push or a pull, something that makes an object move. Now that we have that cleared up, let's talk about Newton's three laws of motion. His first law states that an object at rest tends to stay at rest unless it's acted upon by an unbalanced force. Now, I said unbalanced for a reason there. Right now, there's technically two forces acting on this ball. We have gravity pulling it downward. If I let go, it falls every time. But I'm counteracting gravity with a force of my own. My hand is applying a force upward on the ball, a push that is opposite and equal to gravity, so there's no unbalanced force on the ball. That's why it's stationary. There's no unbalanced force. I'm balancing one. There are no other forces acting on it. Now, a good breeze could come along, imagine it, there you go, and push the ball off of my hand. The breeze would cause an unbalanced force. Or I could simply, take my hand and push it that way and knock over the camera. But an unbalanced force, that's what causes something to change its state of motion. Now, the other thing about Newton's first law, not just things that are stationary, but let's say that it's sailing along out in space. We have to say out in space because on Earth, gravity and air tend to mess things up. Trust me, you don't want to worry about air yet. Anyway, take this object, and if I throw it, it'll try to keep going at that same speed in the same direction until another force acts on it, another unbalanced force. The first unbalanced force that comes to your mind, of course, when you throw something is gravity. And it instantly is pulling on this thing, and it continues to pull on it until it gets down to the ground. But if there were no gravity acting on it, the ball would continue in a straight line, constant speed, until some other force acted on it. And that's Newton's first law of motion. And since it's talking about the property of all matter, anything that has mass, like this ball here, or this rock here, mass is the property of matter that states how much stuff is in it. This has more stuff, and you can take my word for it, than this one does. And it is heavier on Earth. Gravity pulls on things with more mass harder. And therefore this is going to be heavier. But mass and weight are not the same thing. Don't get them confused. If you get confused on those, look in your section. Read the unit that I wrote, and or the module on the unit that I wrote. And hopefully that'll clear that up. But they're two different things. But the property of any mass to continue with its state of motion, either in a straight line or not moving at all, is called its inertia. The property of matter to continue in its state of motion. That's inertia. So we call the first law the law of inertia. Okay, so it's the first law. We gave it a name. It's the law of inertia. Sorry. Really creative name, though. You have to give us that. Second law. We're not going to give it a name at all. Because we love math so much, we're going to give it a formula. Newton's second law is F equals ma. Your book writes F net. Puts a net under there, under the F. Net basically means unbalanced force. So, Newton's second law of motion, if we put it into words, says that a net force is equal to the mass of the object times the acceleration of that object. So, I take it back to this state right here. No unbalanced force is acting on it. I take an unbalanced force and apply it. The acceleration of the ball is proportional to the force that I push it with and inversely proportional to the mass. And if that doesn't make sense, let me write this another way. F equals ma is one easy way to write it and remember it. But if we solve it for acceleration instead, see that acceleration is equal to, divide both sides by m, so we get F over m. Acceleration is equal to the force applied to the object divided by the object's mass. So in other words, I take this object, if I want to accelerate it more, I can apply more force. And it'll go faster. It'll accelerate at a greater rate. Or, if I wanted it to go slower, I could make it more massive. I could apply the same force that I applied to that ball to this rock. I guarantee it's not going to fly as well as that ball is. It takes more force, a greater force, to cause an acceleration on an object with bigger mass. That's how that works. So if m gets bigger, acceleration gets smaller. Just plug some numbers in if you don't see that. If force gets bigger, acceleration gets bigger. So these two vary proportionally. These two are inversely proportional, as we talked about in Unit 1. So bigger mass takes more force to accelerate it. More force means greater acceleration. That's Newton's second law of motion. Third law of motion. Third law of motion's cool. Sorry if I get too close to the camera, I might have bad breath. Newton's third law of motion states that for every force applied, let me back up. Newton's third law of motion, before we start that, always applies to two objects. And I'm going to write that down here underneath. Two objects. Always remember that. Don't try doing Newton's third law of motion with one object. You can't do that. If you do it with one object, it just doesn't work out. Nothing would move or do anything. But anyway, two objects. Newton's third law of motion states that for every force applied, there is an equal and opposite force applied. And remember, we're talking about two objects. So, or, in the words of Newton, action, for every action, there's an equal and opposite reaction. Which I like saying applied force better. For every force that I apply to something, it applies a force back to me. Chalkboard. I push on the chalkboard. No matter how hard I push, the chalkboard is pushing back on me with the same force, but in the opposite direction. I push inward, the chalkboard pushes toward the camera against me with equal force. If it doesn't, then I have a problem. It falls through and I fall on the ground on top of it. So, for every force applied, there's an equal and opposite force applied. Remember, it takes two objects in order to have Newton's third law. It's between two different objects. Actually, all of these require at least two objects, but we'll get to that later. Another example, and I think I use this one in the module. If I have my friend Bob. Hi, Bob. Bob doesn't talk. I have my friend Bob standing over here on a skateboard. Use your imaginations here. I am also standing on a skateboard. Bob is as massive as me. We won't talk about weight. We'll talk about mass. Bob, right here, is looking at me. And Bob says, "Hey, how you doing?" I say, "Hey, fine." And we're good friends, see? And so we can talk to each other like that. And I give him a friendly shove because we're friends and we can do that. And I push Bob. Bob, of course, is on a skateboard. So am I. Bob goes sliding that way because I gave him a shove, sliding backwards. What happens to me? Well, Newton's third law states, I push Bob on the shoulder. Bob's shoulder pushes back on my hand. Therefore, I also slide backwards. Newton's third law of motion. For every action, there is an equal and opposite reaction. Or for every force applied, like me pushing Bob, Bob's body is going to push back on me with equal and opposite force. If you're swimming in the water, some of you might be good swimmers, I don't know yet. I don't know you yet, actually. This is July, but that's okay. But say you're in the water and you're swimming. So you're going along in the water. I give the water a push with my hands, pushing the water back. Well, the water is also pushing me forward. As a matter of fact, when I swim, it's me pushing the water and the water pushing back that causes me to move forward. So Newton's third law of motion applies in a lot of different places. Rockets. When a rocket takes off, the gases coming out of the rocket are being pushed by the rocket. They're also pushing the rocket. So Newton's third law of motion applies in a lot of places. If you have questions about that, you can bring them to class. Otherwise, I think we've covered Newton's three laws of motion. If you understand all that, get to work on the homework. If not, come and see me in class. We'll talk more about it.